They said 3I-ATLAS was nothing, just another comet, a frozen wanderer passing quietly through the void. But then came the silence. Data feeds vanished. Observatories went dark, and NASA declared something that sounded routine. A NASA-wide news lockdown. Routine? Since when does a harmless comet require classified clearance? Every telescope had it in view. Every scientist whispered its name. But what we got instead of answers was noise, denial, deflection and delay. But tonight we put an end to all these. We expose every lie, every cover story, and every manipulated headline. Stay until the end. Because as the truth about 3I-ATLAS finally surfaces, you'll understand why they needed to bury it so deep. If this mystery continues to pull you in the way it does me, make sure to hit like and subscribe so you don't miss a single update as this unfolds in real time. Drop a comment with where you're tuning in from, what time it is there, and whether you believe we're getting the full truth about these world-changing discoveries. And if you want to help this community grow, share this video on X, Facebook, Reddit, or even just in your group chats. You're the reason we can keep chasing stories like this, so thank you for having our back. Part 1. Breaking update. They said it was just a comet. They said it was alien technology. We were misled on both counts. Right now, somewhere between Mars and Jupiter, a visitor from another star system is racing away from our sun. Its name is 3I-ATLAS, and for 4 months it has been the centre of a scientific storm that nobody wants to talk about honestly. On one side, you have the conspiracy theorists screaming about alien probes and hidden spacecraft. On the other, you have NASA and the mainstream astronomy community insisting everything is perfectly normal. Nothing to see here, move along. Both sides are lying to you. Not necessarily with malicious intent, but lying nonetheless through omission, through oversimplification, through the careful framing of what they choose to reveal and what they choose to hide. I'm going to show you something that should make you uncomfortable. Not because it proves aliens are real, not because the world is ending, but because it reveals how easily scientific narratives can be shaped, manipulated and weaponized for attention or for institutional comfort. The timeline alone should make you suspicious. Discovery happens July 1st, 2025. An automated telescope in Hawaii spots something moving wrong, moving too fast, on a trajectory that doesn't belong to anything orbiting our sun. Within weeks, the speculation begins. By early October, you've got Harvard astrophysicists on record raising alarms about unusual chemistry. Then comes the critical window, October 21st through October 30th. The comet approaches perihelion, its closest point to the sun. We're told to wait. We're told it will pass behind the sun, out of view, and that we'll need to wait until November 3rd to see what happens after it emerges. That framing right there, that careful management of expectations, that's where the manipulation begins. Because here's what they didn't tell you. The observations were already showing anomalies before perihelion. The chemistry was already bizarre. The behaviour was already outside the envelope of what typical comets do. And the whole hidden behind the sun narrative? That was never as airtight as they made it sound. Amateur astronomers were tracking it. Ground-based telescopes caught it days before closest approach. The imagery exists. The data exists. But the story being sold to the public was one of mystery, of waiting, of revelation delayed until after the fact. Why? What purpose does that serve? Let me be clear about what this video is and what it isn't. This isn't a conspiracy theory deep dive where I'm going to tell you that 3I-ATLAS is an alien mothership coming to harvest our oceans. This also isn't a whitewash where I regurgitate NASA press releases and tell you to trust the experts. This is a forensic investigation of every major claim made about this object, from the wild to the institutional, and an examination of where those claims hold up and where they crumble under scrutiny. We're going to walk through 5 major lies, what I'm calling lie number 1 through lie number 5, plus 5 timeline manipulation tactics, TL1 through TL5. Each one represents a narrative frame that either exaggerated the threat or downplayed the genuine anomalies. Here's how we'll proceed. First, I'll map out the entire lie tree, every false claim node, so you can see the forest before we examine each tree. Then we'll dive into lie number 1, the alien spacecraft hypothesis, not to debunk it with a hand wave, but to actually examine what that claim rests on, where it's weak, and where, disturbingly, it's not as absurd as you might think. From there we'll tackle size exaggeration, composition oddities, acceleration myths, and impact threat hysteria. Then we'll shift gears into the timeline lies, the messaging strategy that tried to control what you saw and when you saw it. Finally, we'll zoom out and connect this to the broader landscape of recent astronomical discoveries, other anomalies that don't fit the models, and ask what it means when science decides something is solved before all the data is in. The stakes here are higher than you realise. This isn't just about one comet, it's about how we process the unknown. It's about trust in institutions that are supposed to tell us the truth, but often settle for telling us what's convenient. It's about a scientific establishment that is incredibly good at modelling the expected, but struggles when confronted with the genuinely weird. And it's about a public that oscillates between blind credulity and knee-jerk skepticism, because nobody is giving them the full picture. 3I-ATLAS is the third confirmed interstellar object we've ever detected. Only the third. We have almost no statistical baseline for what's normal when it comes to visitors from other star systems. Every assumption we make is built on a sample size of 3. Think about that. Every confident proclamation about what this object should or shouldn't do is extrapolation from a dataset so small it barely qualifies as data. So what are we actually dealing with? What do we know with high confidence? And where does the uncertainty begin? That's what comes next, and I promise you, even the baseline facts are stranger than most people realise. Part 2. Lie Tree Overview. We need a map. Before we dive into each individual deception, you need to see the whole architecture of how these narratives were constructed and how they interact with each other. Let me lay out the lie tree for you. Lie number 1 is the alien spacecraft hypothesis, the claim that 3I-ATLAS isn't a natural object at all, but a probe, a vessel, or some kind of artificial construct deliberately visiting our solar system. Lie number 2 is size exaggeration, the idea that this thing is tens of kilometres across, bigger than any comet we've ever seen, impossibly large for a natural body. Lie number 3 concerns composition, specifically the claim that spectroscopy reveals nickel without iron, an industrial alloy signature that couldn't form naturally. Lie number 4 is about non-gravitational acceleration, the assertion that the object is exhibiting thrust or propulsion beyond what gravity and outgassing can explain. Lie number 5 is the impact threat claim, the notion that 3I-ATLAS poses some kind of collision danger to Earth. Now those are the sensational lies, the ones that get clicks and spread fear, but there's another layer, more insidious, because it comes wrapped in institutional authority. These are the timeline lies. TL1 is the claim that 3I-ATLAS would be hidden behind the Sun at perihelion, invisible to observation. TL2 is the instruction to wait until November 3rd to see what happened after closest approach. TL3 is the implication that any interesting manoeuvres or changes occurred out of view during that supposed blackout window. TL4 is the framing that nothing irregular happened before perihelion, that all observations up until closest approach were perfectly ordinary. And TL5 is the broader narrative that the entire timeline matched expectations for a standard comet. Nothing surprising, nothing to explain. Each of these lies, both the conspiracy-flavoured ones and the establishment-flavoured ones, serves a purpose. The first set generates attention, fear, and engagement. The second set manages expectations, controls the release of information, and protects reputations. What's interesting is how they feed each other. When NASA says nothing unusual, that vacuum of official weirdness gets filled by people speculating about alien probes. When conspiracy theorists make wild claims about size and composition, that makes it easier for scientists to dismiss all questions as fringe nonsense. It's a dynamic that benefits both sides, as long as neither side has to confront the actual anomalies in the data. So what do we actually know? Let's establish the baseline. 3I-ATLAS is the third confirmed interstellar object, following 1I Oumuamua in 2017 and 2I Borisov in 2019. It travels on a hyperbolic orbit, which means it's not gravitationally bound to the Sun. It's passing through, not sticking around. Its closest approach to the Sun occurred around October 30th, 2025, at approximately 1.4 astronomical units. That's just inside the orbit of Mars. Its closest approach to Earth was about 1.8 astronomical units, roughly 270 million kilometres. At no point was there any realistic collision threat. Discovery was made on July 1st, 2025 by the ATLAS survey, an automated sky monitoring system designed to catch fast-moving objects. Here's where things get interesting. We don't actually know how big it is. Hubble observations place the nucleus diameter somewhere between 440 metres and 5.6 kilometres. That's a huge range. The upper limit is roughly 3.5 miles across. The lower limit is less than half a kilometre. Why such uncertainty? Because what we're seeing is mostly the coma, the cloud of gas and dust surrounding the nucleus, and separating the brightness of the coma from the brightness of the bare nucleus is incredibly difficult. When someone tells you definitively that this object is X kilometres wide, they're guessing within a factor of 10. Keep that in mind. Multiple major observatories have been watching this thing. Hubble, James Webb, Swift, Gemini North, Gemini South, Keck, ground-based facilities across the planet. We have early data, but it's incomplete. We're still in the observation phase, still waiting for peer-reviewed analysis of some of the most interesting findings. That delay, that gap between raw observation and published science, that's where narrative control happens. That's where institutions decide what gets emphasised and what gets quietly footnoted. I want to make something absolutely clear before we go further. This investigation is not about denying what science does know. It's about interrogating what's being framed as settled when the evidence suggests it's anything but. It's about recognising that we don't know is a valid and often more honest answer than it's definitely just a comet, nothing weird here. The anomalies are real. The question is whether they're weird within the bounds of natural comet behaviour or weird enough to demand we rethink our assumptions entirely. Now that you've seen the map, let's walk into the first tree, the alien spacecraft hypothesis. Not to mock it, but to genuinely examine what would have to be true for that claim to hold up, and where the evidence actually points. Part 3, lie number 1, alien spacecraft hypothesis. Let's talk about the idea that 3I-ATLAS might be an alien probe. Not because I think it is, but because dismissing the question outright without examining the logic is intellectually lazy. The claim goes like this. 3I-ATLAS arrives on a trajectory that's suspiciously aligned with the ecliptic plane, the flat disk where most of the planets orbit. Its path suggests a deliberate approach, not the random angle you'd expect from an object drifting between stars. Some commentators have pointed out that its velocity and trajectory would allow it to perform what's called a solar Oberth maneuver, a trick where you use the sun's gravity and your close approach, speed, to slingshot yourself into a new trajectory with minimal energy expenditure. It's a maneuver that spacecraft use. Why would a natural comet just happen to arrive on a path that's optimal for that kind of gravitational assist? Then there's the timing. Discovery in July, perihelion in late October, closest Earth approach in between. If you were an alien civilization sending a probe to observe our solar system, wouldn't you want to pass close enough to Earth to gather data, but not so close that you risk collision or detection? The geometry, some argue, is too convenient. Add to that the fact that Harvard astrophysicist Avi Loeb, who previously argued that Oumuamua might be artificial, has been raising questions about 3I-ATLAS's chemistry and behaviour. Media outlets picked up on his concerns. The Times of India ran a piece quoting warnings issued before October 29th. Social media exploded with speculation. You had influencers and independent researchers framing this as a quiet alien probe slipping past our defences, while the establishment pretended everything was normal. So let's stress test that hypothesis. What would we expect to see if 3I-ATLAS were actually artificial? First, we'd expect course corrections, even subtle ones. Spacecraft don't coast on purely gravitational trajectories for months without adjustments. They fire thrusters, adjust orientation, compensate for solar radiation pressure or gravitational perturbations. Has 3I-ATLAS exhibited any course corrections? No credible evidence suggests it has. Its path matches a ballistic trajectory modified only by gravity and outgassing, the same forces that affect natural comets. Second, we'd expect some kind of propulsion signature that doesn't match outgassing. Outgassing is when ice sublimates, turns from solid to gas, and that gas jets away from the nucleus, producing a small reactive thrust. It's messy, asymmetric, and dependent on where the sun is heating the surface. Artificial propulsion would be cleaner, more controlled, likely pulsed or directional in ways that outgassing isn't. Do we see that? No. The non-gravitational forces detected so far, and they're small, match what you'd expect from cometary outgassing. No anomalous thrust, no engine signature. Third, if this were a probe, we'd expect it to be relatively small and dense, not a fluffy ball of ice and dust. But 3I-ATLAS has a coma. It's outgassing. It's exhibiting all the signs of volatile ices sublimating as it gets closer to the sun. Water vapour has been detected. Carbon dioxide has been detected in huge quantities. This thing is behaving like a comet because, as far as all the spectroscopy and imaging can tell, it is a comet. Fourth, let's talk about sample size. We've detected exactly 3 interstellar objects. 3. You can't build a statistical model of what's normal for interstellar visitors from 3 data points. Oumuamua was weird. It had an elongated shape, no visible coma, and exhibited non-gravitational acceleration that some argued couldn't be explained by outgassing. 2I Borisov was much more typical, a clear comet with normal behaviour. 3I-ATLAS is somewhere in between. It's showing comet-like characteristics but with some unusual chemistry and optical properties. Does that mean it's artificial? Or does it mean that comets from other star systems formed in different chemical environments can look and behave differently from ours? We don't have enough data to say which explanation is more likely. Now, here's where it gets uncomfortable. The International Asteroid Warning Network, IAWN, has been monitoring 3I-ATLAS as part of planetary defense protocols. That's the network designed to track objects that could potentially threaten Earth. They're treating it like any other near-Earth object, running the numbers, refining the orbit, making sure it's not a hazard. If there was serious suspicion that this was artificial, if there were any evidence pointing toward non-natural origin, do you think the response would be business as usual? Or do you think there'd be a different level of attention, maybe one we wouldn't hear about publicly? Let me give you the most generous interpretation of the alien probe hypothesis. Suppose an advanced civilization wanted to study our solar system but didn't want to announce their presence. They'd send a probe disguised as a comet. It would outgas, produce a coma, behave in every observable way like a natural object, but internally it would be gathering data, analysing our planet, our sun, our electromagnetic emissions. How would we tell the difference between that and an actual comet? We probably couldn't, not without getting much closer, not without sending a mission to intercept it and examine it directly. And by the time we had the capability to do that, it would already be leaving the solar system, accelerating back into interstellar space. So here's what I'm saying. The alien spacecraft hypothesis isn't disproven. It's unfalsifiable with the data we currently have. That doesn't make it likely. It makes it unprovable. And science doesn't deal well with unfalsifiable claims, but the fact remains that we cannot with absolute certainty rule it out. What we can say is that every piece of observable behaviour matches natural comet physics. The chemistry, while unusual, isn't impossible for a body formed in a different stellar environment. The trajectory, while convenient, isn't so precise that it requires intelligent guidance. The lack of clear propulsion signatures argues against artificial control. But here's the hook. If the composition and polarization data, which we'll get to shortly, continue to defy explanation, if the post-perihelion behaviour shows deviations from models, if future spacecraft happen to pass through its tail and detect something genuinely anomalous, then the conversation changes. Until then, the alien probe theory remains speculation built on the absence of a complete natural explanation. An absence of a complete explanation is not the same as evidence of artificiality. What is clear, though, is that the size and composition claims being thrown around, those are where the next layer of lies lives. Let's go there now. Part 4, lie number 2 and 3, size, exaggeration, and unusual, composition. Some people want you to believe that 3I-ATLAS is a monster, tens of kilometres across, far larger than any comet ever observed. Others want you to believe its chemical composition reveals industrial processes, artificial materials that couldn't exist in nature. Both claims are distortions, but both are rooted in real anomalies that deserve attention. Let's start with size. The claim is that 3I-ATLAS is enormous, perhaps 20 or even 30 kilometres in diameter. Where does that number come from? Early brightness estimates. When something is far away, and you can only measure how much light it reflects, you have to make assumptions about its reflectivity, its albedo. If you assume the object is dark, like a charcoal briquette, then to produce the observed brightness it would have to be very large. If you assume it's brighter, more reflective, then it could be much smaller. Initial estimates before detailed observation sometimes erred on the side of assuming low reflectivity, which inflated the size. That's how you get headlines screaming about a 20-kilometre comet barreling through the solar system. But Hubble changed that. Hubble's high-resolution imaging allowed astronomers to separate the brightness of the coma from the brightness of the nucleus itself. The coma is the cloud of gas and dust that surrounds the solid core. It's huge, often hundreds of thousands of kilometers across, and it's what makes comets look big and bright. But the nucleus, the actual solid object, is tiny by comparison. Hubble's data constrained the nucleus diameter to between 440 meters and 5.6 kilometers. That upper limit, 5.6 kilometers, is roughly 3.5 miles. That's not small, it's a respectably sized comet. But it's nowhere near the 20 or 30 kilometers being thrown around in speculative commentary. Why does this matter? Because exaggerating the size feeds the narrative that this object is unusual, that it's unprecedented, that it must be something other than a comet. The truth is that even at the upper end of the Hubble estimate, 3I-ATLAS fits comfortably within the size range of known comets. It's not record-breaking, it's not impossible, it's just a comet-sized comet. The lie isn't that it's big, the lie is that it's unprecedentedly impossibly big. Now let's talk composition, because this is where things get genuinely strange. James Webb Space Telescope observed 3I-ATLAS using its near-infrared spectrograph, and what it found was shocking. The coma is dominated by carbon dioxide, CO2. The ratio of carbon dioxide to water vapour is approximately 8:1. Read that again. 8 parts carbon dioxide to 1 part water. Typical solar system comets are water-dominated. They're dirty snowballs, mostly water ice with some frozen carbon monoxide, carbon dioxide, methane, ammonia mixed in. But the ratios are nothing like what Webb found in 3I-ATLAS. This thing is a carbon dioxide bomb with some water on the side. Why does that matter? Because it tells us something about where and how this object formed. Comets in our solar system formed in the cold outer regions, beyond the ice line where water freezes, but carbon dioxide freezes at even lower temperatures. If 3I-ATLAS is CO2 rich, it might have formed in an even colder region of its parent star system, or in a system with a different chemical inventory than ours. That's not impossible. That's just alien in the literal sense. It came from another star formed in a different environment, with different conditions. Of course its chemistry is different, but then there's the nickel claim. Some commentary, particularly from Avi Loeb and researchers using Keck Observatory spectroscopy, suggested detection of nickel emission lines, specifically nickel tetracarbonyl, a compound that's produced industrially on Earth. Nickel without iron, an alloy signature. That's the claim that's been latched onto by people arguing for artificial origin. Industrial chemistry happening in a comet. That doesn't make sense unless it's not a comet. Let's slow down. First, the nickel tetracarbonyl detection has not been peer review confirmed. It's preliminary, based on spectral features that could have alternative explanations. Spectroscopy is hard. You're looking at light that's passed through or been emitted by a cloud of gas and dust, and you're trying to identify specific molecules based on the wavelengths they absorb or emit. There's noise, there's overlap, there's ambiguity. Claiming you've definitively detected a specific compound requires rigorous analysis and independent confirmation. We don't have that yet. Second, even if nickel tetracarbonyl is present, does that prove industrial origin? Not necessarily. Nickel is a common element in the universe. Carbonyl compounds, molecules with carbon and oxygen bonded in specific ways, can form in space through natural gas phase chemistry. If you have nickel atoms, carbon monoxide molecules, and the right conditions of temperature and radiation, you can form nickel carbonyl compounds without a factory. It's exotic, it's rare, but it's not impossible. What's more likely is that 3I-ATLAS has an unusual dust composition, maybe because it formed from the remnants of a planetary collision in its home system, or because it's a fragment of a differentiated body that had a metal-rich core. Asteroids can outgas too if they have volatile pockets. Maybe this is a hybrid object, part comet, part asteroid, with properties of both. That would explain the unusual chemistry without requiring alien metallurgists. But here's the uncomfortable part. We don't have a complete natural explanation yet. The CO2 to water ratio is extreme. The polarization signature, which we'll get to, is off the charts weird. The dust properties don't match typical comets. All of that is true. Saying it's just a comet is premature. Saying it's an alien spacecraft is unsupported. The honest answer is that 3I-ATLAS is an interstellar object with chemical and physical properties we don't fully understand, and that makes it scientifically fascinating and frustrating in equal measure. What we need to ask next is whether this thing is accelerating in ways it shouldn't, and whether it ever posed any threat to Earth. Those are lie number 4 and lie number 5. and they're simpler to dismantle than you might think. Part 5. Lie number 4 and 5. Acceleration and threat to Earth. Let's get the easy one out of the way first. 3I-ATLAS is not going to hit Earth. It never was. Anyone who told you it might, anyone who suggested there was collision risk, was either ignorant or lying for clicks. The orbital data is public. NASA's Center for Near-Earth Object Studies, CNEOS, publishes trajectory information for every tracked object. 3I-ATLAS's closest approach to Earth was 1.8 astronomical units, approximately 270 million kilometers. That's farther away than the Sun. At no point did this object's trajectory bring it anywhere near a collision course with our planet. The orbit is hyperbolic, meaning it's not bound to the Sun, it's passing through and leaving. Even if you wanted to steer it toward Earth, you'd need to apply enormous amounts of thrust to change its trajectory. This was never a threat. The impact danger narrative is pure fiction. But the acceleration question is more interesting. Lie number 4 is the claim that 3I-ATLAS exhibits non-gravitational acceleration that can't be explained by natural outgassing, that it's somehow propelling itself in ways that suggest artificial control. Let's unpack that. Comets do accelerate in ways that aren't purely gravitational. When the Sun heats the nucleus, ice sublimates, gas jets away, and that produces a reactive force, like a tiny rocket. This is called non-gravitational acceleration, and it's completely normal for active comets. The tricky part is modelling it. You need to know the shape of the nucleus, where the jets are located, how strong they are, and how they change as the comet rotates and heats unevenly. It's messy physics, and it means that a comet's trajectory won't match a pure Keplerian orbit. There will be deviations, small ones, but measurable. Has 3I-ATLAS shown non-gravitational acceleration? Yes, but only at levels consistent with outgassing. There's no evidence of sudden unexplained changes in velocity. There's no sign of course corrections. The deviations from a purely gravitational path match what you'd expect from mesosymmetric gas jets. Some researchers looked at the dust production rate and found unusual behaviour. A pre-perihelion study by Jewett and Liu measured the power law exponent describing how dust production scaled with distance from the Sun. The value they found, -1.8 plus or minus 0.3, is within the range of other comets but on the steep side, suggesting strong volatile activity even far from the Sun. That's interesting, but it's not propulsion. What would propulsion look like? You'd see delta V changes, velocity changes that don't correlate with solar heating or orientation. You'd see thrust applied in directions that don't make sense for outgassing. You'd see acceleration that continues even when the comet is far from the Sun, and shouldn't be outgassing much. None of that is observed. The acceleration profile matches a comet with unusual, but not impossible volatile chemistry. Here's the speculative angle though. What if, after perihelion, trajectory refinements show an unexpected deviation? What if the orbit changes in ways that models can't account for with outgassing alone? That would be a problem. That would demand explanation. It would reopen the door to alternative hypotheses, including artificial control or some unknown physics. But as of now, we don't have that data. Post-perihelion tracking is ongoing. Orbit refinement takes time. We'll know more in the coming months. The threat narrative and the propulsion narrative both suffer from the same problem. They're built on the absence of complete data and the presence of uncertainty. Uncertainty gets filled with speculation, and speculation gets amplified until it sounds like fact. 3I-ATLAS is not a threat. It's not accelerating beyond what outgassing can explain. But it is behaving oddly in other ways, and those oddities are what we should be focused on. Now we shift gears. We've dealt with the sensational lies, the ones that make headlines and spread fear. Next, we're going into the timeline lies, the narrative framing that told you when to look, when not to look, and what to expect when you did. Part 6, Timeline Lie 1 through 3, Behind the Sun Narrative. Here's where the manipulation gets subtle. It's not about faking data. It's about controlling the story of when you get to see the data and how you're primed to interpret it. Starting in mid-October, as 3I-ATLAS approached perihelion, a specific narrative began circulating. The comet would pass behind the Sun, out of view, and we'd have to wait until after closest approach to see what happened. November 3rd was thrown around as the date when we'd finally get clarity, when the object would emerge from the Sun's glare and telescopes could track it again. The implication was clear. There would be a blackout window, a period where no observation was possible, and whatever happened during perihelion, we wouldn't see it until later. That framing is TL1, the claim that 3I-ATLAS would be hidden behind the Sun at perihelion. TL2 is the instruction to wait until November 3rd to learn what occurred. TL3 is the suggestion that any significant events, any manoeuvres or changes happened during that unobservable window. All three of these are misleading at best and false at worst. Let's start with the geometry. Perihelion occurred around October 30th. At that point, 3I-ATLAS was at its closest to the Sun, about 1.4 astronomical units. From Earth's perspective, was it directly behind the Sun, completely occulted, invisible? No, it was not. The Sun is a finite disk, half a degree across as seen from Earth. For an object to be truly hidden behind the Sun, it needs to be within that narrow cone of occultation. 3I-ATLAS passed close to the Sun in angular terms, meaning it was in the same general direction as the Sun, but it was not directly behind it. Observers with the right equipment, telescopes with solar blocking filters, and ground-based facilities in favourable locations could and did track it. Amateur astronomers reported observations in late October. Images from Gemini North and Gemini South show the comet around October 25th, days before perihelion. The Teide Observatory captured time-lapse composites. This was not a hidden object. It was difficult to observe because of the Sun's glare, but difficult is not impossible. The blackout window narrative was overstated. Why does this matter? Because if you're told that nothing can be seen during the critical period, you stop asking for data from that period. You accept that there's a gap and you wait for the post-perihelion reveal. But the gap was smaller than advertised. Observations were possible, and observations were made. The question is why the public framing emphasised the blackout rather than the continuity of observation. TL2, waiting until November 3rd, compounds this. Why November 3rd? That's nearly a week after perihelion. If observations were possible before and during close approach, why the delay in releasing findings? Part of the answer is scientific caution. Researchers want time to analyse data, to model what they're seeing, to make sure their conclusions are sound before going public. That's reasonable. But it also creates a window where narrative control is possible. If you tell people to wait a week, you have a week to decide how to frame what you found, what to emphasise, what to downplay. TL3 is the most insidious. The suggestion that anything interesting happened out of view, during a window when telescopes couldn't track the object, that plants the seed of mystery. It implies that the most significant moments, the potential for unexpected behaviour, occurred when no one was watching. But if observations were continuous, if we have data from before, during and after perihelion, then that implication is false. The timeline was observable. The anomalies, if any, were visible. What actually happened in that window? Jewett and Liu's pre-perihelion development study shows brightness changes, morphological evolution of the coma, and unusual dust production behaviour starting well before perihelion. The tail structure changed. The dust fan shifted from sun-facing to anti-solar earlier than some models predicted. These are not things that happened in secret. These are things that were observed, measured and published. So why the blackout framing? Maybe it's innocent. Maybe it's scientists hedging their bets, not wanting to make claims until they're certain. Or maybe it's a form of narrative management, a way to control public expectation and avoid premature speculation. Either way, the effect is the same. It creates the impression of hidden knowledge, of secrets revealed only when the authorities decide you're ready to hear them. The timeline lies aren't about what happened. They're about when you're allowed to know what happened, and that should bother you more than any of the wild speculation about alien probes. Part 7. Timeline Lie 4 and 5. All normal, until perihelion and standard comet timeline. Let me tell you what you were supposed to believe. Up until perihelion, everything about 3I-ATLAS was proceeding as expected. It brightened as it got closer to the Sun, exactly like a comet should. Its dust production increased, its coma expanded, all perfectly normal. The only question was what would happen at closest approach, whether it would survive the intense solar heating or break apart. That was the narrative. Everything normal until perihelion, then we'll see. That's TL4, and it's a lie by omission. The anomalies didn't start at perihelion. They were there from the beginning, visible in the data, but downplayed or ignored in public communication. Let's walk through what was actually observed before perihelion and why it matters. Jewett and Liu's study of pre-perihelion development covers observations from mid-October through late October, well before closest approach. They measured the dust production rate and how it scaled with distance from the Sun. For a typical comet, this relationship follows a power law, and the exponent tells you how strongly the comet responds to solar heating. They found an exponent of negative 1.8 plus or minus 0.3. That's steep. It means the comet was producing dust at a rate that increased rapidly as it approached the Sun, faster than some models predicted. They also measured the dust ejection velocity, how fast particles were leaving the nucleus. The values were consistent with comet activity, but the overall behaviour suggested a body that was unusually volatile rich, possibly with a higher than expected fraction of carbon dioxide ice that sublimates more vigorously than water ice. This is consistent with the JWST findings we discussed earlier, the CO2-dominated coma. But it means the comet was already behaving unusually, already showing signs of exotic chemistry, weeks before perihelion. The morphology changed too. Early images showed a broad, sun-facing dust fan, the kind of structure you see when dust is pushed away from the nucleus by solar, radiation pressure. But as the comet got closer, the fan collapsed into a more collimated antisolar tail, a structure pointing away from the Sun. That transition happened earlier than expected for some models. It's not catastrophic, it's not proof of anything artificial, but it's a deviation from the simplest expectations. Brightness fluctuations were also noted. The comet didn't brighten smoothly. There were periods of rapid increase followed by plateaus. That could indicate rotational effects where different parts of the nucleus with different compositions get exposed to sunlight as the comet spins. Or it could indicate episodic outbursts, sudden releases of gas and dust from fractures or pockets of volatile material. Either way, it's not the smooth, predictable brightening curve you'd expect from a textbook comet. None of this was hidden. It's in the literature, in preprint papers, in observational logs. But it wasn't emphasized in public messaging. The story sold to the general public was, wait and see what happens at perihelion, not, we're already seeing unusual behavior, and we're trying to figure out what it means. TL5 is the broader claim that the entire timeline matched expectations for a standard comet. It didn't. The chemistry was anomalous, the polarization was anomalous, the dust production behavior was on the edge of the expected range. The claim that this was a standard comet following a standard timeline is defensible, only if you cherry-pick the data and ignore the outliers. And in science, the outliers are often where the most interesting discoveries happen. Why frame it as normal when it wasn't? Because calling it anomalous invites questions that might not have satisfying answers yet. It opens the door to speculation, to criticism, to demands for more data and more analysis. It's easier to say, everything's fine, nothing to see here, than to say we're seeing things we don't fully understand and we need more time to figure it out. But the second statement is the honest one. The timeline lies, all 5 of them, are about narrative control. They're about managing public perception, about deciding what gets emphasized and when, about framing uncertainty as certainty, because certainty is easier to communicate and harder to question. But when you peel back that framing, what you find are anomalies that demand explanation. Real, measurable deviations from expectation that can't be hand-waved away with, it's just a comet. Now, we're going to go deeper. We're going to look at the specific anomalies that make 3I-ATLAS genuinely strange, the chemistry and the light-scattering properties that don't fit any simple model. This is where the science gets uncomfortable, where even the experts start hedging their language. Part 8. Deep Anomaly, Carbon Dioxide-Rich Coma and Polarimetry Oddities. There are 2 observations about 3I-ATLAS that should make any astronomer stop and pay attention. The first is its chemical composition. The second is how it scatters light. Both are outside the normal range for comets, and both suggest that either this object formed in a radically different environment than solar system comets, or we don't understand comets as well as we thought we did. Let's start with the carbon dioxide. James Webb Space Telescope pointed its near-infrared spectrograph at 3I-ATLAS and measured the composition of the coma, the cloud of gas surrounding the nucleus. What it found was a carbon dioxide to water ratio of approximately 8:1. For every molecule of water vapour, there were 8 molecules of carbon dioxide. That is extreme. Solar system comets typically show the opposite pattern. Water dominates, with carbon dioxide, carbon monoxide, methane and other volatiles present, but in much smaller amounts. You might see a CO2 to water ratio of 0.1 or 0.2, maybe 0.5 in a really carbon-rich comet. But 8? That's off the scale. Why does this matter? Because it tells you about the temperature and chemistry of the environment where this comet formed. Water ice condenses at relatively warm temperatures, cosmically speaking. You can form water ice in the outer solar system, beyond the frost line, where temperatures drop below roughly 270 Kelvin. But carbon dioxide requires even colder conditions, or a gas disk with a very different composition than the one that formed our solar system. If 3I-ATLAS is CO2 dominated, it likely formed in the outer reaches of its parent star's protoplanetary disk, or in a system where carbon was more abundant relative to oxygen and hydrogen. JWST also detected other species: carbon monoxide, carbonyl sulfide, water ice grains in the dust, silicates. The full inventory is complex and still being analysed, but the dominance of carbon dioxide is the headline finding. It's not impossible. It's just rare to the point of being unprecedented in our direct observations of comets. Now, you could argue that this simply reflects the diversity of planetary systems. Not every star forms planets and comets the same way. Different metallicities, different disk temperatures, different radiation environments, all of that affects the final composition of the bodies that form. 3I-ATLAS came from another system, so of course it's different. That's a reasonable argument, but it also means we can't just assume that interstellar comets will behave like solar system comets. Every assumption built on our local sample might not apply. Then there's the polarimetry. This is where things get truly weird. Polarimetry measures how light is polarized, how the electric field oscillates in specific directions when it scatters off particles. For comets, this tells you about the size, shape, and composition of the dust grains in the coma. Different grain properties produce different polarization signatures. A preprint paper titled "Extreme Negative Polarization of New Interstellar Comet 3I-ATLAS" reported something that shouldn't exist according to standard comet models. The comet exhibits a deep, narrow negative polarization branch at small phase angles. Phase angle is the angle between the Sun, the comet, and the observer. At small phase angles, you're looking almost directly back at the Sun through the coma. Most comets show a region of negative polarization in that geometry, but it's usually shallow, a few tenths of a percent. 3I-ATLAS shows negative 2.7% at small phase angles. That's an order of magnitude stronger than typical. What does that mean? It suggests that the dust grains in the coma are either much larger, much more porous, or much more compositionally homogeneous than typical comet dust, or some combination of those factors. Large, fluffy aggregates of small particles can produce strong negative polarization through a process called coherent backscattering, where light waves interfere constructively when scattering back toward the source. But the specifics of the grain size distribution and composition needed to produce the observed signature are unusual. Compare this to 2I Borisov, the second interstellar object. Borisov had a polarization signature that was nearly identical to solar system comets. It was unremarkable. It fit right into the expected range. 3I-ATLAS doesn't. It's an outlier, and a significant one. Why does this matter? Because polarimetry is one of the few ways we can probe the physical properties of dust grains remotely. We can't collect samples from 3I-ATLAS. We can't send a spacecraft to scoop up dust and bring it back. All we can do is measure the light it scatters and infer the properties of the scatterers. If the polarization signature is anomalous, it means the dust is anomalous. And if the dust is anomalous, it might mean the formation history is anomalous. Let me speculate for a moment. What if 3I-ATLAS didn't form in a protoplanetary disk at all? What if it's a fragment of a planetary collision, a piece of a destroyed world that got ejected from its home system at high velocity? That could explain the unusual composition. A planet or large moon that differentiated, separated into layers of rock and ice and possibly metal, and then got shattered by an impact. The fragments would have compositions that don't match typical comets. They'd have whatever layers happen to be in that piece of the original body. If you shattered an icy moon with a CO2-rich mantle, you'd get chunks that outgas carbon dioxide preferentially. That's speculation. But it's grounded speculation, based on the anomalies we're actually seeing. It's an alternative to just saying weird comet from weird system, nothing more to explain. Because the polarimetry and the chemistry together suggest something genuinely unusual about this object's history. It's not just a comet. It might be a comet-like object, with a non-cometary origin story. There's one more angle to this, and it's one that almost nobody's talking about publicly. The possibility that spacecraft currently in flight, missions that have nothing to do with 3I-ATLAS, might accidentally fly through its tail and give us in-situ data we weren't expecting. Part 9. Hidden Angle, Spacecraft Interactions and Tail Crossing. Here's something that didn't make the headlines but should make you curious. At least one spacecraft currently operating in the inner solar system may pass through or near the extended tail of 3I-ATLAS. I'm not talking about a dedicated flyby mission. I'm talking about an accidental encounter, a spacecraft on its way to somewhere else that happens to intersect the debris stream left behind by the comet. Comet tails are enormous. The visible tail you see in images, that's just the densest part. The actual stream of particles can extend for millions or even tens of millions of kilometres, a diffuse ribbon of dust and ionized gas trailing behind the nucleus. Any spacecraft that crosses that path, even far from the nucleus itself, could detect it. Dust impact sensors would register hits. Charged particle detectors would see elevated counts. Magnetometers might pick up perturbations in the solar wind. Even if the spacecraft wasn't designed to study comets, it would gather data. Europa Clipper, NASA's mission to Jupiter's moon Europa, launched in October 2024. It's currently on a cruise trajectory that will take it through the inner solar system multiple times for gravity assists. I don't have confirmation that its path crosses 3I-ATLAS's tail, but the possibility exists. Other missions, Mars orbiters, solar observatories, any spacecraft operating in the right region at the right time could encounter the tail. Why does this matter? Because in situ measurements are the gold standard. Everything we know about 3I-ATLAS so far comes from remote observations. We're looking at light, analysing spectra, measuring brightness and polarisation. But we're not touching it. We're not sampling the gas and dust directly. If a spacecraft flies through the tail, and its instruments record the composition, the particle size distribution, the ionisation state, that data would be orders of magnitude more precise than anything we can get from telescopes. What could that data reveal? It could confirm or rule out the nickel tetracarbonyl detection. It could measure the carbon dioxide to water ratio directly, without the ambiguities of spectroscopy. It could tell us the size and structure of the dust grains, resolving the polarimetry anomaly. It could detect trace species, rare molecules that are below the detection threshold for remote observation. And if there were anything genuinely anomalous, anything that didn't fit natural processes, in situ sensors would be the ones to catch it. There's a flip side to this, though. Spacecraft instruments have limited sensitivity. They're designed for specific purposes, and comet tail measurements might not be a priority for their operations. Data gets recorded, but it might not get analysed immediately. It might sit in an archive for months or years before someone thinks to look at it. And if mission planners don't anticipate the encounter, they might not activate the right instruments at the right time. Then there's the question of data release. When spacecraft make unexpected discoveries, how quickly does that information become public? There are protocols, peer review processes, mission timelines. If a spacecraft did detect something unusual in 3I-ATLAS's tail, would we hear about it in weeks, months, or years? And if the finding were genuinely strange, something that didn't fit expectations, would there be pressure to withhold it until it could be explained? I'm not suggesting a conspiracy. I'm suggesting that the machinery of institutional science moves slowly, and that the gap between measurement and publication is a window where control over narrative is possible. If you're NASA, and one of your missions accidentally detects something weird in an interstellar comet's tail, do you rush to announce it, knowing that it will trigger speculation and headlines and demands for more data? Or do you take your time, analyse it thoroughly, make sure you understand it, and release it when you're ready to contextualise it properly? The answer depends on what you value more: speed or accuracy, transparency or reputation, public curiosity or scientific caution. There's no obviously right answer, but the choice affects what we know and when we know it. Let me paint a hypothetical scenario. Suppose Europa Clipper crosses the tail in late November. Suppose its dust impact detector registers hits with an unusual composition signature. Suppose the data suggests a higher nickel content than expected, or an unexpected organic molecule, or particle sizes that don't match the remote observations. That would be significant. That would demand explanation. But would it be announced immediately? Or would it be held until the team could model it, until they could rule out instrumental error, until they could frame it in a way that didn't invite wild speculation? You see the problem. The most important data might exist already, recorded by instruments that weren't looking for it, waiting for someone to notice, and we, the public, wouldn't know until someone decided to tell us. This brings us to the bigger question. When does scientific caution become institutional gatekeeping? When does the desire to avoid sensationalism become the suppression of legitimate anomalies? That's the meta-debate we need to have, and it's bigger than just 3I-ATLAS. Part 10. Meta-debate, scientific openness versus conspiratorial framing. Let's zoom out. This isn't just about one comet, it's about how science handles the unknown, how institutions manage public communication, and where the line is between responsible skepticism and premature closure. I want to introduce 3 more lies, but these aren't lies in the sense of factual falsehoods. These are framing lies, narrative choices that shape how you think about the evidence before you've even seen it. I'll call them Lie C, Lie D, and Lie E. Lie C is the claim that there's no need to consider alien origin, because natural explanations are overwhelmingly likely. This sounds reasonable on its surface. Occam's razor, the principle that the simplest explanation is usually correct, suggests we shouldn't invoke aliens when comets will do. But the problem is that overwhelmingly likely is a judgment call, and it depends on how you weight the anomalies. If you focus on the aspects of 3I-ATLAS that match typical comets, then yes, natural origin seems obvious. But if you focus on the anomalies, the carbon dioxide dominance, the polarimetry, the pre-perihelion behaviour, then overwhelmingly likely starts to feel less certain. The framing of Lie C discourages investigation. It says, we already know the answer, it's natural, no need to waste time on exotic hypotheses. But science progresses by investigating the unexplained, not by assuming the expected. If every anomaly is dismissed as probably just natural variation, then we never discover the genuinely new. Lie D claims that 3I-ATLAS's size, trajectory and speed are well within natural limits, nothing anomalous. We've already addressed the size exaggeration, and shown that the object is comet size, not impossibly large. The trajectory is hyperbolic, consistent with an interstellar origin, and the speed is within the range expected for objects ejected from other star systems. So far, so good. But the framing that nothing is anomalous ignores the chemistry and the polarimetry. It cherry-picks the aspects that fit and discards the aspects that don't. This is a subtle form of dishonesty. It's not lying about the data. It's lying about the significance of the data. It's saying, look, everything important is normal, and those weird details over there, those don't matter. But what if those weird details are the most important part? Lie E is the big one. The claim that we know enough now to stop debating, that the case is closed, it's a comet, end of speculation. This is the ultimate narrative control move. It says, we've looked, we've analysed, we've reached a consensus, and the consensus is that there's nothing unusual here that requires further explanation. Any continued questioning is fringe, conspiratorial, anti-science. But the data doesn't support that closure. We have ongoing observations, we have papers in preprint that haven't been peer-reviewed, we have instruments still gathering data, we have spacecraft that might provide in situ measurements. The investigation is not over, the case is not closed. Claiming that it is serves one purpose, to shut down inquiry. Why would institutions want to shut down inquiry? Not because they're hiding aliens, but because uncertainty is uncomfortable. It invites criticism, it opens the door to speculation, it makes the public question expertise. It's easier to project confidence, to say we've got this figured out, than to admit that we're still learning, still unsure, still surprised by what we're finding. There's a historical parallel here. When Oumuamua, the first interstellar object, was discovered in 2017, it exhibited strange behaviour. It had no visible coma, no obvious outgassing, but it showed non-gravitational acceleration. Avi Loeb proposed that it might be an artificial light sail, a thin reflective sheet propelled by radiation pressure. The mainstream astronomy community pushed back hard. They argued that outgassing from a thin layer of hydrogen ice, which wouldn't produce a visible coma, could explain the acceleration. That explanation became the accepted one, even though it required some special pleading about the ice's properties. Was Loeb right? Probably not. But was the pushback motivated purely by the data? Or was it also motivated by a desire to avoid the stigma of entertaining alien hypotheses? The reaction to Loeb's proposal was often dismissive, sometimes hostile. It sent a message. Don't speculate about aliens, even when the data is ambiguous, because that's not serious science. That precedent affects how 3I-ATLAS is being discussed. Researchers who see anomalies and want to explore unconventional explanations know that they risk their reputations by doing so publicly. It's safer to stay within the bounds of conservative interpretation, to frame everything as unusual but natural, than to say openly that we don't have a good explanation yet. But science shouldn't be about safety. It should be about truth. And truth sometimes requires entertaining uncomfortable possibilities, not because they're likely, but because they're not yet ruled out. Let me ask you a question. Are you comfortable calling an object just a comet when we cannot explain its chemistry, its polarization signature, or its unusually strong outgassing far from the sun? Are you comfortable with authorities telling you that the case is closed when observations are ongoing and data is still being analysed? If the answer is no, then you understand why this investigation matters. Now let's connect this to the broader pattern of astronomical surprises in the past year. 3I-ATLAS isn't the only thing challenging our models. There are discoveries across the board, from galaxy dynamics to exoplanet formation to solar system oddities, that suggest our understanding of the cosmos is incomplete. Let's look at a few of them. Part 11. New discovery. Dwarf galaxy gas bridge in Virgo cluster. In late 2025, astronomers announced the discovery of a massive faint gas bridge connecting two dwarf galaxies in the Virgo cluster. NGC 4532 and DDO 137 are separated by hundreds of thousands of light years, but they're connected by a stream of hydrogen gas that's barely visible, detectable only through sensitive radio observations. This wasn't predicted. Models of galaxy interaction suggested that gas stripping should leave tails and streams, but not bridges of this scale and faintness between such small galaxies. Why am I telling you about galaxies when we're supposed to be talking about a comet? Because the pattern is the same. We build models based on what we've observed, we extrapolate those models to new situations, and then reality surprises us with something that doesn't fit. The gas bridge is anomalous. It challenges our understanding of how dwarf galaxies interact, how gas is stripped and exchanged, how the intergalactic medium evolves, but nobody's calling it impossible. Nobody's saying it can't be natural. Instead, astronomers are revising their models, looking for mechanisms they might have overlooked, expanding the parameter space to accommodate the new observation. That's exactly what should be happening with 3I-ATLAS. When you find an object with chemistry and polarimetry outside the expected range, the response should be curiosity, not dismissal. It should be an invitation to refine the models, to explore new formation scenarios, to ask what other surprises might be waiting. But instead, we get narratives about how it's just a comet. Nothing to see here. Move along. The gas bridge challenges galaxy models at a large scale. 3I-ATLAS challenges comet models at a small scale. Both are telling us that the universe is more diverse, more complex, more full of edge cases than our theories anticipate. Both deserve the same level of intellectual humility. Here's the uncomfortable truth. Science operates on the assumption that the majority of objects will fit the models, and the outliers are rare exceptions that can be explained with minor tweaks. But what if the outliers are more common than we think? What if we're biased towards seeing the things that fit and ignoring the things that don't? Observational selection effects are real. We discover what our instruments are sensitive to, and we miss what they're not. The gas bridge was there all along. It took new radio surveys with better sensitivity to find it. How many other faint, unexpected structures are out there, waiting for someone to look in the right way? 3I-ATLAS might be the same. It might be genuinely unusual, a rare type of object that we haven't seen before because we've only detected 3 interstellar visitors total. Or it might be typical of interstellar objects, and our solar system comets are the weird ones, biased by the specific conditions of our star's formation. We don't know. We can't know until we have a much larger sample. But framing it as solved, as just another comet, forecloses that line of inquiry. The galaxy discovery teaches us something else. Anomalies at any scale can be harbingers of deeper gaps in our knowledge. Astronomers studying galaxy clusters now have to revisit their assumptions about gas dynamics. Maybe comet scientists need to do the same. Part 12. New discovery. Exoplanets in strange environments. Let me tell you about another recent surprise. Astronomers have been discovering exoplanets, planets around other stars, for nearly 3 decades now. We've found thousands. We've characterized their orbits, their masses, their atmospheres. We thought we had a decent handle on planet formation theory. Then we found Earth-sized planets in environments where they shouldn't exist. TOI 2267, for example, a binary star system where two stars orbit each other closely, and somehow Earth-sized planets formed in orbits that exposed them to brutal radiation and tidal forces. Standard planet formation models say this shouldn't work. The environment is too chaotic, too hot, too hostile. Planetsimals, the building blocks of planets, should have been scattered or vaporized before they could grow large enough to survive. Yet there the planets are, orbiting, existing, defying expectation. Why does this matter for 3I-ATLAS? Because it's another example of the universe not reading the textbook. We expect planets to form in stable, relatively cool, metal-rich disks around single stars. When they don't, when they form in binaries or close to their stars or in low metallicity environments, it forces us to expand our understanding of what's possible. The same applies to comets. We expect comets to be water-rich, dirty snowballs because that's what solar system comets are. When an interstellar comet shows up with 8 times more carbon dioxide than water, it's telling us that comet formation is more diverse than our local sample suggests. Could 3I-ATLAS have formed in a system like TOI 2267, a binary or a high radiation environment that produced unusual volatile inventories? Could its parent star have been a different spectral type than the Sun, cooler or hotter, changing the temperature gradient in its protoplanetary disk? Could it have formed farther out, in the Oort cloud equivalent of another system, where temperatures were cold enough to preferentially trap carbon dioxide over water? These are the questions we should be asking. Not, is it natural or is it alien? But, what natural processes could produce what we're seeing, and what do those processes tell us about the diversity of planetary systems? The exoplanet discoveries teach us that planets are resourceful, that they form in places and ways we didn't anticipate. Comets probably are too. There's a deeper point here. Every time we find an anomalous planet or an anomalous comet or an anomalous galaxy structure, we're mapping the edges of the known. We're finding the boundary between what our theories predict and what actually exists. Those boundaries are where new physics lives. Those boundaries are where the next generation of discoveries will come from. If we treat every boundary case as just a weird exception, we miss the opportunity to learn something fundamental. 3I-ATLAS is a boundary case. Its chemistry, its polarimetry, its behaviour, all of it is pushing the edge of what we thought we knew about comets. That makes it valuable, not suspicious. It makes it an opportunity, not a threat. But only if we're willing to investigate it openly, without predetermined conclusions about what it must be. Part 13, New Discovery, Quasi-Moon of Earth, 2025, PN7. In the opening months of 2025, the night sky offered astronomers something unexpected, a faint, slow-moving point of light whose orbit didn't belong to any catalogued satellite, asteroid or fragment of space debris. It was subtle, a barely perceptible drift across the background stars, but its motion didn't quite match the known patterns of near-Earth objects. For weeks, observatories tracked it, refining its orbit with every observation. Then, as the data settled, the realization dawned. This object wasn't a new asteroid in a typical near-Earth orbit. It was something much rarer. Not a true moon, not gravitationally bound to our planet like the familiar Luna we see each night, but something stranger, a quasi-satellite, sometimes called a quasi-moon. Its designation, 2025 PN7. From our perspective on Earth, this small rock appears to loop around us in a long, graceful arc. Over the course of months and years, it seems to trace an intricate path, as if it's orbiting Earth directly. But that's an illusion, a projection born of orbital resonance. In truth, 2025 PN7 is orbiting the Sun, not Earth. Yet its orbital period, the time it takes to make one complete circuit of the Sun, matches Earth's almost exactly. This synchrony creates a gravitational partnership, a 1-1 resonance. Imagine two runners on the same track circling at the same speed, but on slightly different lanes. From the stands, one might appear to drift ahead or fall behind, looping closer, then farther away. That's how a quasi-moon behaves, caught in a celestial rhythm, forever dancing near Earth but never truly bound to it. Its path, depending on your vantage point, looks like a vast horseshoe or a spiralling corkscrew around our planet's orbit. Over decades, these objects seem to hover, drift, and reverse. their motion guided by the subtle tug of gravity from both the Earth and the Sun. Astronomers estimate that PN7 will remain in this delicate configuration for decades, possibly centuries, before slowly migrating away under the influence of solar and planetary perturbations. This phenomenon is rare, but not unprecedented. Earth has a few known quasi-satellites, 2003 YN107, which stayed with us for several years before escaping. Kamoa-Alawa 2016 H03, still accompanying us today, and 469219 2016 H03, nicknamed Earth's constant companion. Each of these is a small body, a few meters to tens of meters across, insignificant in mass, but rich in scientific intrigue. They occupy a fragile gravitational niche, a region where the balance between Earth's and the Sun's gravity allows temporary companionship without capture. When 2025 PN7 was first logged, it triggered a momentary burst of confusion. Its trajectory was almost Earth-like, but not identical. Its brightness varied unexpectedly. Some of its early positional data hinted that it might be larger than the typical near-Earth asteroid. Speculation spread quickly across astronomer forums and social media. Could it be a piece of space debris from the Apollo era, nudged into a resonant orbit by a lunar flyby? Could it be a spent rocket up a stage like the 2020 ESO incident, when an old Centaur booster temporarily masqueraded as an asteroid? Or, as some less cautious voices suggested, could it be something deliberately placed there? For a brief week, the question hung in the air. Then, the data began to arrive. Spectroscopy, analysing the reflected sunlight across wavelengths, revealed a spectrum consistent with silicate-rich rock, the same kind of minerals found in other S-type near-Earth asteroids. No traces of paint, no metallic alloys, no telltale signs of manufactured surfaces. Its orbit, once refined with additional observations, was fully explainable through gravitational perturbations and solar radiation pressure. No exotic propulsion, no unexplained accelerations. The conclusion was clear. 2025 PN7 was natural. An ordinary fragment of space rock, temporarily caught in a complex gravitational waltz with Earth. The object itself wasn't the revelation our reaction was. Every time something behaves in a way that defies expectation, humanity slips into the same rhythm. Curiosity ignites, fear follows. Then come the stories. When the boundaries of known behaviour blur, we fill the gaps with narrative. Some imagine danger, a hidden threat, a rock on a collision course, a weapon in disguise. Others imagine agency, that it's controlled, artificial, a watcher, a messenger. Still others imagine conspiracy, that the truth is known but withheld, locked away behind bureaucratic silence. It's the same cognitive reflex that makes constellations from stars, gods from lightning, and meaning from coincidence. Ambiguity is intolerable, so we explain, and that's the first great lesson of 2025 PN7. The sky can deceive not through intention, but through complexity, and our minds rush to impose order. That same psychological playbook unfolded again later that year, on a much grander scale, with the arrival of 3I-ATLAS, the third known interstellar object. When data showed its unusual chemistry, high CO2 ratio, and extreme negative polarization, speculation exploded. Was it an alien probe, a shard of interstellar technology, or simply a natural object shaped by conditions foreign to our solar system? The evidence was ambiguous enough to feed every interpretation. Scientists leaned toward the natural explanation. Theorists and enthusiasts kept the door open for the extraordinary. NASA's official line, that it was a cometary interstellar object showing unexpected behaviour, satisfied the cautious but frustrated the curious. The polarised scatter of light, the pre-perihelion brightness anomalies, the asymmetric dust jets, all of it invited questions that outpaced the data. The pattern was identical: ambiguity, speculation, polarisation, narrative warfare. 3I-ATLAS became a Rorschach blot for our beliefs about life, science, and institutional trust. And once again, the anomaly wasn't just in the sky, it was in us. The quasi-moon story resolved quickly. Within a month the data settled, and the scientific community moved on. But in that efficiency lies another danger: the premature closing of curiosity. Had astronomers dismissed 2025 PN7 outright after the first few nights, they might have missed subtle details, the way sunlight pressure slightly altered its trajectory, or how its orbital resonance provides clues to the long-term stability of Earth's co-orbital companions. These quasi-moons, though small, are invaluable testbeds for studying the boundary between capture and escape, the fine line between a stable moon and a passing wanderer. They inform mission planners about orbital resonances that could one day host space stations or telescope platforms in quasi-stable configurations. In other words, the mundane rock turned out to have hidden value, but only because scientists kept watching after the excitement died down. This patience, this refusal to let the story end too soon, is exactly what the 3I-ATLAS investigation needs. Yes, the simplest explanation is that it's natural. Yes, the chemistry, dynamics and polarization might eventually fit updated cometry models once we understand interstellar dust better, but that probably must be tested, not assumed. Science thrives on discomfort, on keeping the door open just wide enough for truth to slip through, even when it's inconvenient. The question then becomes, why did the quasi-moon story fade quietly while 3I-ATLAS became a cultural event? Part of it is scale. 2025 PN7 is a pebble. 3I-ATLAS is a celestial visitor from another star, but the deeper reason is emotional weight. A quasi-moon doesn't threaten our worldview. It doesn't carry existential implications. It doesn't invite us to imagine intelligence beyond Earth. It's just a rock, following the laws of gravity. 3I-ATLAS, on the other hand, sits at the crossroads of science and mythology. It brushes against ancient longings, the idea of messengers from the stars, of alien artifacts, of cosmic omens. It connects to Oumuamua and Borisov, to Avi Loeb's controversial papers, to every conversation we've had about whether we are alone. It matters to us. And when something matters, we interpret data differently. We frame uncertainty as mystery, and mystery as meaning. That emotional gravity pulls scientists, journalists, and the public alike into orbit. Even when the data is clean, the narrative remains turbulent. In both stories, the quasi-moon and the interstellar visitor, we see the same undercurrent: confirmation bias. When people want something to be true, they collect evidence selectively. When they fear something, they dismiss the same evidence as flawed or manipulated. Astronomers know this, but even they are not immune. Bias doesn't always shout. Sometimes it whispers. It shapes which hypotheses we test first, which anomalies we ignore, which explanations we find satisfying. In the case of PN7, bias pushed toward the prosaic. The idea of another piece of space debris felt familiar, safe, expected. Once ruled out, the community exhaled and moved on. In the case of 3I-ATLAS, bias pushed both ways, the skeptics toward dismissal, the believers toward fascination. Both camps drew strength from uncertainty, but neither owned it completely. The lesson here is balance between skepticism and wonder, between dismissal and belief. The cosmos is not obliged to fit our expectations. Sometimes what looks artificial is natural. Sometimes what seems ordinary hides revelation. The quasi-moon reminds us to be humble before complexity. We now know that quasi-satellites could become stepping stones for future exploration. Their proximity and predictability make them ideal candidates for robotic missions, resource studies, even staging points for deep space telescopes. But none of that would have emerged had we written them off as curiosities. Likewise, 3I-ATLAS may one day force a revision of cometry models, perhaps showing us that interstellar objects form in colder, CO2-dominated disks, or that light scattering in alien dust behaves differently. Or perhaps it will simply fade into history, another solved mystery. Either outcome is valuable if we stay patient enough to learn. What unites these stories is a call for intellectual resilience. When data conflicts with expectation, we must resist the urge to collapse it into the nearest comfortable category. It's just a comet. It's definitely alien. Both statements end inquiry. Neither embodies curiosity. The middle ground, we don't know yet, is uncomfortable. It demands we live with ambiguity. But that's where science breathes. As new telescopes like the Vera C. Rubin Observatory come online, as AI systems scan terabytes of sky data nightly, anomalies will multiply. The universe will seem stranger by the day. Some of those strangenesses will be noise, some will be errors, and a few will be revolutions waiting to happen. When that flood arrives, we'll need to remember 2025 PN7, the rock that fooled us for a moment and reminded us how quickly curiosity turns to certainty. Because the next time, the anomaly might not fade so neatly. The next quasi-moon might not be a rock. The next interstellar object might not behave like anything we've seen before. And when that day comes, we'll face the same choice. Rush to declare what it is, or pause long enough to understand what it means. 2025 PN7 is, by every metric, an ordinary asteroid. But it carries a quiet lesson, that the most extraordinary revelations often hide inside the ordinary, waiting for patience, persistence, and open-mindedness to reveal them. When we first found it, we saw a mystery. Then we saw a rock. But maybe, in that process, we also saw a mirror, a reflection of how humanity confronts the unknown. And perhaps that's why stories like this matter. Because every time we find a new object in the sky, what we're really observing is ourselves, our fears, our hopes, our need to make sense of chaos. So, as we turn our telescopes back to the stars, as we chase 3I-ATLAS and whatever follows it, we should carry the humility of the quasi-moon. To keep asking, even when the answers are unsatisfying. To stay curious, even when the experts say the mystery is solved. To hold open the possibility that the next anomaly might rewrite everything we think we know. The universe is vast, our ignorance vaster still. But within that ignorance lies our greatest strength, the refusal to stop looking up. Part 14, New Discovery and Theme, Dark Era Radio Waves and Dark Matter Probes. Let me take you to the edge of the observable universe, to a time before stars, before galaxies, before light itself. The cosmos was once silent. A sea of hydrogen stretched in every direction, cooling, collapsing and waiting. There were no suns to warm it, no gravity wells bright enough to shape it, no starlight to reveal it. This was the cosmic dark era, a period of quiet anticipation when the universe held its breath. Just hydrogen gas, drifting and clumping in the endless dark. And yet, even in that darkness, there was a whisper. Each atom of hydrogen occasionally flipped its spin, a subtle quantum transition that released a photon of radiolight at 21 centimeters wavelength. Those photons, the faintest hum of the young universe, have been stretching through space for 13 billion years, their wavelength elongated by the expansion of the cosmos. And now, for the first time in human history, astronomers are detecting them. It's hard to describe how faint these signals are. Imagine listening for the rustle of a single leaf, while standing next to a hurricane. The foreground noise from our own galaxy, from Earth's radio, stations, from satellites, from the atmosphere itself, drowns everything. The signal-to-noise ratio isn't 1 in 100, it's 1 in a trillion, and yet with arrays like Hera in South Africa, LOFAR in Europe, and the upcoming square-kilometre array, we are beginning to separate those whispers from the storm. We are hearing faintly the echo of the universe waking up. Why does this matter for 3I-ATLAS, an interstellar comet racing past our sun? Because the techniques we use to find those ancient signals, the data processing, the machine learning, the statistical anomaly detection, are about to transform how we look for the unknown in everything else. We are entering the age of algorithmic discovery, an era where human eyes are no longer enough. In the past, astronomy advanced through observation. Someone looked through a telescope and noticed something strange, the wobble of a planet, the dimming of a star, a comet that shouldn't exist. But now, the sky has become too vast. Telescopes like the Vera Rubin Observatory will image the entire visible sky every 3 nights, generating tens of terabytes of data per day. No human can keep up with that. Instead, algorithms will decide what's worth noticing. AI systems trained on millions of examples will scan the night sky pixel by pixel, comparing, correlating, flagging. They will whisper to us, "This one looks different. This one doesn't fit." That's exactly what 3I-ATLAS is, something that doesn't fit. Its polarization behavior, the way sunlight scattered off its dust particles, doesn't match any known comet in the database. Its negative polarization was too deep, too sharp, too persistent. Its coma composition was skewed toward carbon dioxide in ways that defy current models of where such an object could form. If we had fed the entire cometary polarimetry catalogue into a machine learning algorithm and asked it, "Find me the weirdest one," 3I-ATLAS would have been the top hit. It's an outlier, and outliers are where discovery lives. But here's the paradox. As our detection tools grow more powerful, we are now finding more anomalies than we can explain. And that's dangerous, because when anomalies outpace understanding, we're forced to choose what to believe before we truly know. Do we trust the algorithm, the black box of code that tells us something is unusual? Or do we trust the human instinct that says it's probably just noise? That tension between automation and intuition is the new frontier of science. We've seen it before. The Large Hadron Collider at CERN generates petabytes of particle collision data every second. AI filters decide in real time which events might contain new physics and which can be safely deleted. Entire potential discoveries could be vanishing forever in those milliseconds, unseen, unrecorded, discarded by pattern recognition models that never learned what unknown physics looks like. The same dilemma faces dark matter research. Experiments like Lux Zeppelin and Xenon T rely on machine learning to detect faint flashes in ultra-pure detectors deep underground. They're looking for 1 in a billion events, tiny deviations from background noise. Sometimes those algorithms flag anomalies that look like signals, and months later they turn out to be nothing, a faulty sensor, a neutron reflection, a statistical mirage. So how do we know when a signal is real? How do we separate what's meaningful from what's meaningless? This question now defines every field, from cosmology to AI safety to the study of interstellar objects like 3I-ATLAS. Because 3I-ATLAS is real. It exists. It's been tracked. It's been measured. But the behaviour we've seen doesn't fully align with the models we built for comets. Its trajectory follows a hyperbolic path, consistent with interstellar origin, yet its composition looks more like something formed near a CO2 frost line, colder, further out, perhaps from another star's outer disk. Its jet orientation and pre-perihelion brightness spike are unlike any solar system comet, recorded in the same thermal range. So what's going on? Is this simply a natural interstellar fragment, the equivalent of cosmic driftwood, that just happens to look weird because it comes from a different stellar nursery? Or are we seeing a hint of something our models don't yet include, a new class of object, a new process, a new kind of chemistry? The truth is, we don't know. And that's what makes it exciting. This is where science meets humility. When Galileo first pointed his telescope at the sky, he saw moons orbiting Jupiter and craters on the moon, things the official narrative of his time said were impossible. When Jocelyn Bell discovered pulsars in 1967, the first thought her team had was that it might be an alien signal. They jokingly called it LGM-1, Little Green Men. Later it turned out to be a natural astrophysical phenomenon, a rotating neutron star. But notice what that story tells us. Even the greatest discoveries begin as anomalies. Every time we've expanded our observational reach, we've encountered phenomena that didn't fit. At first we call them errors, then we call them anomalies, and eventually we call them new physics. Maybe 3I-ATLAS is just another step in that pattern, but it's also a mirror reflecting how we handle uncertainty. When someone says, it's just a comet, without addressing the inconsistencies, that's not science, that's comfort. When someone else declares, it's alien, without data to rule out natural causes, that's not discovery, that's projection. Both are forms of impatience. Both cut the process short. Science is slow by design. It's the art of not knowing, done carefully. And that's what's being tested in our age of data overload. Because when AI begins finding patterns faster than humans can interpret them, there's a temptation to leap, to take the algorithm's word as proof, or to dismiss it out of hand. Neither is safe. The balance between skepticism and imagination will define whether this next century of science is an age of discovery or an age of confusion. In dark matter physics, machine learning models are now so good that they can identify faint energy deposits deep in detectors buried under mountains. But they're also so sensitive that they flag everything. Cosmic rays, thermal noise, even the mechanical vibrations of the detector itself. The result? Dozens of possible signals, each requiring months of human analysis to confirm or debunk. Sound familiar? That's exactly what's happening with 3I-ATLAS. Every telescope that looked at it reported slightly different readings, slightly different spectra, slightly different coma brightness. When you're dealing with something faint, distant, and moving fast, every calibration error compounds. The data begins to blur the line between real and artifact, and yet anomalies persist. Polarimetry doesn't lie easily. Polarized light carries fingerprints of geometry, grain structure, and composition. If 3I-ATLAS's polarization is extreme, that means its surface dust or coma particles are fundamentally different from those of typical comets. It's not just a data glitch, it's physics. So maybe the anomaly is telling us something profound about how material forms in other star systems. Maybe the chemistry of alien comets reflects their parent star's unique conditions, different metallicities, different radiation fields, different magnetic histories. Maybe, in studying interstellar comets, we're not just learning about rocks and ice, we're sampling the diversity of planetary systems across the galaxy. This is where the dark era radio signal story becomes a metaphor. The universe in its infancy was a place of pure potential, structure emerging from noise. To detect that structure, we have to believe there's a signal there worth finding, and to separate it from the noise, we need both technology and patience. The same applies here. 3I-ATLAS might be a cosmic false alarm, an object that looks strange because of observational biases or geometric coincidences, or it could be a true anomaly, an emissary from a region of space whose chemistry challenges our understanding of how stars and planets form. The only way to know is to keep observing, keep testing, and, crucially, to stay uncomfortable. Because discovery doesn't come from certainty, it comes from doubt. So where does this leave us? In the coming decade, AI-assisted telescopes will monitor the sky in real time. They'll flag objects that brighten unexpectedly, comets whose polarization curves deviate, transits that don't match exoplanet models. They'll find hundreds, maybe thousands, of new anomalies every year. We will have to choose what to follow up on. And we will have to build a culture that values investigation over dismissal, uncertainty over premature conclusions. The age of anomaly fatigue is coming, when scientists bombarded with too many weird detections begin to tune them out. That would be a tragedy. Because among those thousands of false alarms, one could be the real thing, the next Oumuamua, the next pulsar, the next hint of new physics. So the story of 3I-ATLAS isn't just about one comet. It's about how we, as a species, deal with the unknown in an age where the unknown is multiplying faster than we can interpret it. Do we rush to label every anomaly as either normal or alien? Or do we learn to live in the space between, the place where curiosity and patience coexist? If the dark era radio signals taught us anything, it's that the universe rewards those who listen quietly, who wait long enough to separate the whisper from the noise. 3I-ATLAS might be another whisper. It might fade into background noise, or it might grow into something that reshapes our understanding of how interstellar matter behaves. Either way, it's telling us something about physics, about discovery, and about ourselves. Because the truth is, science isn't just about finding answers. It's about learning how to see the unknown without fear. The universe is full of whispers. Hydrogen lines from the dawn of time, gamma flashes from distant galaxies, comets that defy our models, data points that don't fit the curve. And each time, we're faced with the same question. Do we look away because it doesn't make sense, or do we look closer? Time, and more data, will tell. But if there's one lesson from both cosmology and 3I-ATLAS, it's this. The universe always leaves clues, and sometimes those clues are wrapped in anomalies, things that don't fit because they're pointing the way to something new. So maybe the next great discovery won't come from a headline, a telescope, or a scientist staring at a screen. Maybe it will come from an algorithm, quietly flagging a data point that doesn't belong, and maybe, just maybe, that anomaly will be the moment we finally understand what's been hiding in the cosmic noise all along. Part 15. Wrap and Forward Outlook. What might we learn next? Let's bring this home. What have we learned, and where do we go from here? 3I-ATLAS is an interstellar comet with unusual properties. Its carbon dioxide to water ratio is extreme, approximately 8:1, far outside the range of typical solar system comets. Its polarimetry signature shows deep negative polarization at small phase angles, a feature rarely if ever seen in other comets. Its pre-perihelion behavior showed early dust production and morphological changes that deviated from the simplest models. Its trajectory brought it close to the Sun but posed no threat to Earth, and its existence as only the third confirmed interstellar object means we have almost no statistical baseline for what's normal. What we don't know is whether these anomalies represent a genuinely new class of object, a formation environment radically different from our solar system. or whether they're just the extreme tale of natural comet diversity that we haven't sampled well, because our local population is biased. We don't know if the nickel tetracarbonyl detection is real or an artifact. We don't know if future polarimetry will continue to show unusual behaviour, or if it was specific to the phase angles and distances observed so far. We don't know if post-perihelion monitoring will reveal unexpected changes in activity or trajectory. What we've exposed in this investigation are the lies, both sensational and institutional, that shaped public perception of this object. The alien spacecraft hypothesis, unsupported by evidence but not definitively ruled out. The size exaggeration, based on misunderstanding of coma versus nucleus brightness. The composition claims, some real, some speculative, all incompletely understood. The acceleration myths, confusing natural outgassing with artificial propulsion. The impact threat hysteria, never justified by the orbital data. And then the timeline lies, the claim that the comet would be hidden behind the sun, when observations were possible throughout the critical window. The instruction to wait until November 3rd, managing expectations and controlling when information was released. The framing that nothing unusual happened before perihelion, when anomalies were visible weeks before closest approach. The narrative that the entire timeline matched standard comet behaviour, when deviations were measurable and published. All of these lies, whether told for clicks or for institutional comfort, serve to obscure the genuine scientific questions. They polarise the conversation into believers versus skeptics, aliens versus nothing to see here, when the real question is much more interesting and much more nuanced. What can 3I-ATLAS teach us about the diversity of planetary systems, the chemistry of interstellar environments, and the limits of our current comet formation models? Looking forward, several things will matter. Post-perihelion observations will continue through December 2025 and into 2026. Monitoring the comet's brightness, its coma morphology, its dust production rate, and its trajectory will tell us if perihelion altered its behaviour in unexpected ways. Any deviation from predicted outgassing-driven motion would be significant. Spacecraft tail crossings, if they occur, could provide in-situ data on composition and particle properties. We may not know for months whether any mission encountered the tail or what their instruments recorded, but that data, if it exists, would be invaluable. Future ground-based campaigns, polarimetry, spectroscopy, high-resolution imaging will refine our understanding of the dust and gas properties. Peer review of the preprint papers currently circulating will either confirm the anomalies or reveal observational biases that explain them away. The International Asteroid Warning Network and the Minor Planet Center will continue tracking and cataloguing data. The question is how much of that data becomes public quickly, and how much sits in institutional archives waiting for someone to analyze it. Bigger picture implications loom for interstellar object science. If 3I-ATLAS becomes the first case where we cannot comfortably fit it into standard comet models, that changes the conversation. It means the next interstellar visitor, and there will be more, will approach it with less confidence and more humility. For SETI and speculative search communities, should anomalous interstellar comets become a formal category of interest? Not because they're likely to be alien, but because they're not yet fully explained, and unexplained phenomena deserve investigation. For science communication, this case study reveals the tension between conservatism and openness. How do you balance the need to avoid sensationalism with the need to admit uncertainty? How do you tell the public that something is weird without triggering panic or conspiracy theories? There's no easy answer, but defaulting to nothing to see here when anomalies exist is dishonest. Let me leave you with this. If we stay curious, if we question narrative framings, if we inspect the shadows behind the sun instead of accepting that they're empty, we may yet uncover evidence that changes our model of what's normal in the cosmos. 3I-ATLAS is either a standard comet from an unusual environment, or it's something we don't have a category for yet. Either answer is interesting. Either answer expands our understanding. The lies told about this object from both sides, from the sensationalists and from the establishment, reveal something important about how we process the unknown. We're uncomfortable with ambiguity. We want answers now, clean narratives, certainty. But the universe doesn't owe us certainty. Sometimes the most honest thing science can say is, we don't know yet, and that's fascinating. 3I-ATLAS passed perihelion on October 30th, 2025. It's now moving outward, heading back toward interstellar space. In a few years, it will cross the orbit of Jupiter. In a decade or two, it will be beyond Neptune, fading from view, impossible to observe even with our best telescopes. This was our one chance to study it up close, and the data we gathered will be analysed for years to come. Papers will be published, models will be refined, arguments will be had in conference halls and in peer review. But the public narrative, the story most people will remember, has already been written. For some, it will always be the alien probe that NASA covered up. For others, it will be just another comet, nothing special, overblown, by conspiracy theorists. Both stories are wrong. Both miss what actually happened. What actually happened is that an object from another star system, formed in conditions unlike anything in our solar system, passed through our neighbourhood and showed us that the universe is stranger and more diverse than our theories predicted. It showed us that carbon dioxide can dominate water in a comet's composition. It showed us that polarimetry signatures can fall outside the known range. It showed us that our sample size of 1, our own solar system, our own comet population, is not a sufficient basis for understanding what's out there. The real story of 3I-ATLAS isn't about lies, it's about limits. The limits of our knowledge, the limits of our models, the limits of our ability to explain the new in terms of the familiar. Every interstellar visitor pushes those limits a little further. Oumuamua showed us that interstellar objects don't always look like comets. Borisov showed us that sometimes they do. 3I-ATLAS showed us that even when they look like comets, they can behave in ways that demand new explanations. And that's the hook I want to leave you with. We're living in a moment where the rate of astronomical discovery is accelerating. New telescopes, new instruments, new surveys, all of them finding things we didn't know existed. Interstellar objects, exoplanets in impossible orbits, faint structures connecting galaxies, radio signals from the cosmic dawn. Every one of them is a challenge to our understanding. Every one of them is an invitation to revise our models, to expand our thinking, to admit that we're still learning. The question is whether we'll accept that invitation, or whether we'll retreat into comfortable certainty, whether we'll investigate the anomalies or dismiss them, whether we'll tell the truth about what we don't know or pretend we have all the answers. 3I-ATLAS gave us data. What we do with that data, how we interpret it, what questions we ask next, that's up to us. The object itself is already gone, racing away from the sun at tens of kilometers per second, carrying its secrets back into the darkness between stars. We had 4 months to observe it, from discovery in July to perihelion in October to post-perihelion monitoring in November and December. That window's closing. The opportunity to gather more data is fading with every passing day. But the mystery isn't closed. The case isn't solved. The lies have been exposed, yes, but the truth remains elusive. And maybe that's the point. Maybe the lesson of 3I-ATLAS is that not every mystery gets a neat resolution. Maybe some things remain strange, not because they're alien, but because the universe is vast and complex and full of edge cases that don't fit our categories. If you take nothing else from this investigation, take this. Question the narratives you're given. Look at the data yourself when you can. Recognise that both sensationalism and institutional reassurance can be forms of deception. Stay curious, stay sceptical, stay open to the possibility that the next discovery, the next interstellar visitor, the next astronomical anomaly, might be the one that genuinely changes everything. 3I-ATLAS won't be the last interstellar object we detect. There will be more, dozens, eventually hundreds as our surveys improve and our telescopes get more sensitive. Each one will be an experiment, a test of our models, a window into the diversity of planetary systems across the galaxy. Some will be ordinary, some will be strange, and one of them someday might be genuinely inexplicable, might force us to confront possibilities we've dismissed as science fiction. That day isn't today. 3I-ATLAS, for all its anomalies, fits within the expanded envelope of natural processes, even if we don't understand all the details yet. But it's a reminder that the universe is under no obligation to behave according to our expectations. It's a reminder that weirdness is not evidence of impossibility, and that the gap between what we expect and what we observe is where discovery lives. So watch the sky. Watch for the next announcement of an interstellar visitor, the next object with a hyperbolic orbit and a strange spectrum. Watch how the narrative unfolds, how the lies get told, how the institutions respond. Learn to recognize the patterns of deception, the framing devices, the rhetorical moves that shape perception before evidence is even examined. And when they tell you it's just a comet, Nothing to see here. Ask yourself if they've earned that certainty. Ask yourself if the anomalies have been explained or just ignored. Ask yourself what's being hidden, not in some conspiratorial sense, but in the sense of what's being left unsaid, what's being downplayed, what's being deferred for later analysis that may never come. The cosmos doesn't reveal its secrets easily. It doesn't hand us answers wrapped in certainty. It offers us data, ambiguous and incomplete, and challenges us to make sense of it. 3I-ATLAS offered us data that doesn't quite make sense yet. The carbon dioxide dominance, the polarimetry anomaly, the pre-perihelion deviations, all of it points towards something we don't fully understand. Not aliens probably, but something. A formation environment we haven't modelled, a chemical process we haven't considered, a physical mechanism we haven't discovered. That something is the prize. That something is what makes this object worth studying, worth debating, worth investigating long after the headlines fade. The lies told about 3I-ATLAS, from every side, every angle, every agenda, those lies tried to give you premature closure. Tried to tell you the story was finished before the data was even collected. This investigation is my attempt to reopen that closure, to show you that the questions are still live, the evidence still incomplete, the conclusion still provisional, to give you permission to be uncertain, to be curious, to demand better explanations than trust us, we've got this figured out. Because if there's one thing 3I-ATLAS proved beyond doubt, it's that we don't have it figured out. Not completely. Not yet. Maybe not ever. And that's not a failure. That's the beginning of real understanding. That's where science lives, in the uncomfortable space between ignorance and certainty, between speculation and proof, between the known and the unknown. Stay in that space. Question everything, and watch what comes next. Because the universe isn't done surprising us. Not by a long shot.